everyone. I'm just like looking out at the crowd. It's absolutely incredible to see such a large group of people. So I'm here to talk about the proposed adaptive metadata tree structure for the V4 Iceberg spec. Brief intro. I'm Amogh. I'm an engineer at Databricks. I primarily work on Apache Iceberg and other open table format related projects. So kind of a quick rundown of what we're going to be talking about today. I'll start out with like a recap of what the metadata tree structure looks like today. I suspect a lot of this audience may be pretty familiar with that, but I think it's useful context to see where we're at today, what are the improvements that we can do, and why this proposed structure is a net improvement for the representation of the project. And then I'll talk about like next steps for V4 and beyond. So yeah, this is kind of like the canonical image of the Iceberg metadata tree today. So at the ground level in the tree, you have the data layer, so data files stored in object storage. Essentially, at the next layer, you're going to have manifests, which point to those data files. And then you'll at the next layer, you're going to have manifest lists, which are pointers to the manifests. And so in this talk, you're going to hear me refer to this part as the content metadata tree. And so at the very root level of an Iceberg table is a metadata file, which keeps track of snapshots, which represent points in time in the table state. And essentially, every snapshot refers to a manifest list. And above this, you have a catalog that's keeping track of metadata files and is responsible for performing the atomic swap of metadata files, and it is responsible for a lot of basically Iceberg's essentially ACID guarantees, or the atomic part of Iceberg's guarantees. So I didn't go into it on the previous one, but essentially one thing we should cover, and we'll see why, where there's areas of improvement, is particularly on metadata rights. So what happens today in a commit? So first, writers will produce whatever data files that they need to as part of their write, and Iceberg also has this notion of merge on read for deletes, so they could also produce delete files, which encapsulate like which positions in files or which predicates which files based on predicates have to be deleted. And so once that is produced by writers, generally. After that, a metadata write is performed where first new manifests are written, where each manifest will refer to those data and delete files. And then a new manifest list is written, which will refer to those new manifests. And in the case of an Iceberg REST catalog, a client will produce and send the snapshot to the server, asking it to perform the commit. And the server will produce a new metadata file and atomically update its internal state to point to that new file. So this is the case of the Iceberg REST catalog. If you're not using Iceberg REST, the client itself would write the file and call a service to atomically update the file pointer. So if you kind of observe, if you kind of imagine, like if you're doing like a fairly small-sized write where you're only producing a handful of data files, this might seem like a lot of metadata writes that are kind of happening. So the metadata write amplification is higher than probably necessary. So you could see, because we have to produce these manifest structures, and we have to produce another manifest list which refers to these manifest structures. So arguably that for these small writes, we are writing proportionally higher metadata than may be really required. So primarily, this kind of shows up in cases where we're doing more small, frequent writes, typically more streaming side workloads. So another thing to kind of notice is what exists today in manifest lists and manifests. So if we kind of look in a zoomed-in view, particularly I would like us to focus on the statistics. On the left side, JSON is a representation of what exists in manifest lists today, a condensed view. And effectively, there are partition summaries which encapsulate the range of partitions a given manifest will span, And these partition summaries are used in pruning. For example, in this example, it's like October 20th, 2025 to October 25th, 2025. And a query which has a predicate where the date is October 21st, we know that we have to read this manifest. The partition summaries are used for that level of pruning. But if you observe, there's no column stats that are kind of rolled up here. And so that's one area of improvement as well. It's like we could actually also additionally store a column stats and get more effective pruning based on column stats rather than just relying on partition information. If you look on the right side, we do have, the right side is for manifests. On the right side, we have partition information, and we have lower and upper bounds for stats, in this case, like an ID-based range. And so we kind of have this, I would say, inconsistency or discrepancy between what stats are maintained at each level in the tree. And if you were to imagine rolling up aggregate column stats, we could get more effective pruning. Another thing I'll mention, this is just a JSON representation just for like presentation purposes. These will be Avro files today, and one of the challenges in that representation is that for these stats, we are currently storing essentially a mapping of the field ID to like a binary representation of the stats, and without any like type information. And so what that means is things like type promotion are a little bit difficult because we don't actually know the original type of the stats. Also the row-based orientation of Avro isn't necessarily efficient for storing sequential stats, whereas if you were to store them in a columnar representation, the structure would be more compressible, and also because it's columnar and we're typically only going to be projecting a certain amount of fields, we know that we only need to project the fields for a given manifest entry. We just need to project the very specific fields rather than project the whole entry. So there's all kinds of basically pruning kind of optimizations that we can do. So that gets us into what the kind of proposed structure is for the V4 adaptive metadata tree. And so if we put everything I just said together, we're doing probably more metadata writes than we really need to for small writes. We could be doing better on the stats storage and the actual representation of manifests. We kind of arrive at these kinds of improved structures. So we could reduce metadata write amplification and latency for small writes by allowing these data and delete files to just be directly written to a root manifest. So in the proposed structure is called a root manifest, but the root manifest in this proposed structure is effectively a logical replacement of what's today called the manifest list. And so you could imagine that this root manifest is essentially like a buffer where you can put not just manifests like today, you can also put data and delete files, and periodically, of course, we cannot shove everything into the root manifest, so over time you would flush out and rebalance to lower layers in the tree. And the second thing is it's really a single representation of manifests at every level in the tree. So what I mean by that is today, like I said, there's this discrepancy. You have this very discrete manifest list structure and then manifests. But really, in this proposed structure, it's all just manifests. There are requirements for what specific entries can go into a root manifest and what's allowed in the leaf manifest, so to speak. And so more specifically, we could actually store stats at every level in the tree and have a very consistent manifest representation. On top of that, these manifests ideally should be columnar to get the benefits of compressibility, be able to do specific column pruning, so you could project just the specific stats that are required during planning. And so there's still some further improvements that we can do for write amplification. So effectively, today, whenever you have a manifest and certain entries need to be replaced, the kind of typical example is you have a delete manifest with DVs, and there's heavy churn on these DVs, and they're frequently being replaced. So you could, today, what happens is these manifests are updated in a copy on write fashion. But what we could take the kind of learnings that kind of exist at the data file level, where we have merge on read style delete files, and we can actually apply them to higher levels in the metadata tree. So specifically, we can have this notion of a manifest deletion vector. And what this means is we can encode which positions and manifests themselves need to be deleted. And so this reduces write amplification because we could basically inline content like a roaring bitmap representation of which positions are deleted just directly in the root manifest. Yeah, it's drawn as a separate box here, but it's actually not a separate file. That's just like for a diagram purpose. Lastly, if we think about like downstream systems from these tables, from writes that happen on these tables, there's a lot of desire to do incremental computations for things like materialized view maintenance, and we could definitely improve the current structure by allowing for efficient change detection. And I'm going to go into each one of these separately and in more detail, but for the change detection, the ideal property is we should be able to ideally look at a snapshot and figure out which paths to traverse to figure out what are the added data files, added delete files, remove data files, remove delete files, and any replaced DVs. And we should ideally not have to do what happens today, which is basically diff between two snapshots. So that's something that would be an ideal property in the new structure. Yeah, so let's zoom in on the single file commits. So effectively, the idea is writes are buffered in the root manifest, which again is basically a logical replacement of the manifest list that exists today. And so when the manifest grows beyond a certain threshold, its contents will be flushed to leaf manifests, and there will be pointers to those leaf manifests in the root manifest as well. It's probably typically referred to as a rebalancing. Large writes will just behave just as they do today. So writers can still, if you're doing very large batch writes, it's pretty much no different than it is today. Just write manifests and then update the root manifest to point to those manifests. Yeah, so in this example here, effectively, it's just showing that you can kind of do writes at different levels in the tree. So you start at snapshot 1, you have a leaf manifest, then we're going to do a data file addition of data file 4, and we can just add that to the root manifest. So now we're just doing a single write and committing to the table, right, at the content metadata tree portion. And so effectively, and the same thing for data file 5, that can also fit in the root in the next snapshot. So we're effectively avoiding, compared to today, the additional manifest that would need to be written in each of these cases. So as I mentioned, another big part of this is columnar manifests and stats representation. In the community today, it's a different proposal, but I think it's really important to zoom in here because this is a very core primitive of the proposed tree structure. A lot of the design around the tree structure is kind of contingent on having a effective columnar representation, and it would affect benchmarking and that kind of stuff. So yeah, the idea with columnar manifests is we could store, particularly stats, we could store in a struct keyed off field ID, and we get the benefits of a columnar structure at the metadata level. So better metadata footprint. Again, you can just project which fields are desired. So even if you have a fairly wide table and you're only reading 1 or 2 columns, instead of today where we have to read this map that contains stats for things that aren't really relevant, we just need to project which fields we want. And we get to keep the type information, the original type information, so this will enable things like better type promotion as well. Yeah, so another core idea is around manifest deletion vectors. So these are, the goal here is to further reduce write amplification. So today, manifests are always rewritten in a copy on write fashion. So imagine you have this table, and you're either doing frequent overwrites of data files or frequent replacements of DVs. those manifests on every snapshot are like frequently being rewritten. And so even if you only are like modifying a handful of files, the metadata write, again, is still a little bit disproportional to the size of the actual like logical write. So we can further improve this by basically taking the lessons of like merge on read style deletion vectors that happen at the data layer in the table and applying that at the metadata layer as well. And so we could use inline DVs. We're doing like a lot of benchmarking on the representation of these like roaring bitmaps, or like how do they actually compress when you like basically lay out roaring bitmaps sequentially. Essentially, you can use that to basically represent which positions are deleted, and that reduces the overall, like, you essentially eliminate the manifest rewrite cost. Of course, I think one thing I glossed over is these manifest DVs can only exist in the root. And one thing I'll emphasize is this proposed structure is still a 2-level tree. So what I mean by that is there's still a root manifest, and the furthest depth it can go to is just having a leaf manifest. Leaf manifests cannot have more leaf manifests. This is kind of a conscious, I guess, design choice behind the proposal, because essentially we want to prevent writers from doing potentially like bad things. So example is if you allow kind of unbounded height in the tree, a writer to do more efficient writes could essentially just keep stacking up writes on top of each other, and basically you get this like skewed tree. So you can imagine like a linked list of manifests, and that really kills planning, because effectively you don't get any parallelism. If you want to read the leaf, if you have to read any files in the leaf manifest, you have to traverse that whole basically linked list. So that's something we want to kind of avoid. And that requirement drives a lot of the requirements for what can be put in a root manifest or not. One thing I'll also emphasize is just like DVs or any kind of delete files at the data file level, at some threshold, it's probably worth just rewriting the manifest. If you have a very high delete ratio, it's probably not worth just keeping that DV around. You probably want to rewrite that. You probably want to pay the price of rewriting that manifest. Another core idea I would say in the proposal is this notion of affinity between data and delete manifests. So currently, this kind of gets into the weeds of like how planning works in Iceberg, but there's effectively a 2-phase planning to match deletes and data files. So what I mean by that is today, an engine has to load up delete files. It can do, going back to one of the first slides, like it can prune based on partition information in the manifest list, but it has to still load more deletes than needed into memory, index them, and then once we figure out which data files we need to read, then we have to go back into that in-memory index and look up which deletes might need to be applied. And so this kind of planning is a little expensive, primarily because you just have to load a lot more than necessary. So there's like I/O, and then there's also like the in-memory cost of building this index. And so one of the ideals is if we can try to essentially reduce the cost of this 2-phase planning. So one way to do this is we have a 1-to-1 correspondence between delete and data manifests, and that can kind of eliminate a lot of these challenges in 2-phase planning. So there's a picture on the next slide that'll make this more clear. But the idea is, if I have a data manifest with files A, B, and C, and I have a delete manifest that has affinity to that data manifest, the delete manifest would contain deletes for A, B, and C. And so what this buys us is essentially we can actually leverage column stats for pruning. So what this means is we can do like a parallel, like co-located planning. So if I read data that data manifest, I know specifically which delete manifests that need to be read, as opposed to today where we're significantly overreading which delete manifests need to be read. So essentially reduce the cost of planning as well. And it could still be done in parallel. And yeah, if you prune out a whole manifest, the data manifest, you know that you don't need to read the equivalent, the delete manifest with affinity as well. Now, one challenge with affinity is maintaining it on write. So you can imagine now that we allow writes to the root, if you have a DV that gets written to the root and there's a delete manifest that also has a delete file on that data file at the leaf level, when we later have to go and write out and flush out and rebalance the tree, we might have to end up paying the price for writing out that delete manifest to maintain that affinity, and that might be higher write amplification at that point. So that's why it's proposed as optional affinity. Essentially, you generally try to keep the writes with affinity, but writers have the option to write delete manifest without affinity, just like today. That allows for flexible writing patterns as well, and then maintenance can kick in and maintain that affinity in the background. Yeah, so this is the diagram. So effectively, in this example, we'll have data manifest 1, which with data files 1, 2, and 3. There'll be delete manifest 1, so that has affinity to data manifest 1, and so we have DVs on the corresponding data files. Same thing for data manifest 2 and files 4, 5, and 6. And so during planning, the benefit now is we know exactly what delete manifests to read based on which data manifests have files that we want to read. And so instead of having to load up delete manifest 1 and 2 and index in memory, we know specifically which manifest to read. And so, like I said, though, this is still optional. So if you want to have flexible writing patterns, manifests can be written without affinity as well. Yeah, so like I mentioned in the beginning, another desirable property is to be able to do efficient change data detection. And so ideally, we want to be able to look at snapshots and figure out what are the new file additions and removals and replacements. And so we ideally want to avoid having to do diffs between snapshots. That's pretty expensive. There's a lot of state reconstruction, and the algorithm can be fairly complex when you have to do diffs across snapshots. So to kind of facilitate this in the new structure, one kind of simple thing we realized that we could do is require deleted manifest entry statuses to be written. So today, there's a little bit of open area in the spec where essentially it's not explicitly required for writers to write out a deleted status when a file is actually deleted from the tree. Today, if an operation comes in and removes a file for whatever reason, in the new manifest, it would just leave out that file. It's not explicitly marked as deleted. And that is a big driver in why diffing has to happen, is because there's lack of existence of that entry in the new snapshot, then you have to compare against the previous snapshot, as opposed to having an explicit status where if that status is explicit, then you know that it changed in that snapshot, and then in the subsequent snapshot, you ensure that it's removed. So that's a simple thing that I think that's being proposed would be proposed at the spec level to make as a writer requirement. Now, one thing that makes change data detection still complicated, I would say, in the new structure is that changes can happen at different levels of the tree. Yeah, I actually want to give Stephen Wu a shout out. He's actually been doing a lot of the diagrams in the proposal here. Yeah, thanks. This is actually one really complicated case, but essentially, yeah, as I mentioned, a lot of the complexity is handling changes across manifest, basically handling the fact that writes can happen at any level in the tree, and on top of that, with this notion of manifest DVs, there's a little bit even more complexity. So that we're trying to kind of work through. So in this example, with manifest DVs, we can mark a position is deleted. So in this example, like we have a snapshot with a data manifest, and then the next snapshot will add a manifest DV to mark one of the positions in the leaf manifest as deleted. And basically, okay, we know that there's a new deletion, so we know that that's one potential change to the state of the table. That things become trickier on the next snapshot that also removes a position in the in the data manifest. It removes position 2 in the data manifest. There's a few choices here. So we could either keep basically manifest DV1 with an added status, and in the first snapshot and the second snapshot, you'd have a new manifest DV, and then the old manifest DV would be added, would be removed, and essentially, and so you could do diffing between the manifest DVs, or we could actually maintain an explicit diff DV, which codifies which new positions for a manifest DV have been deleted. So the trick is, how do you maintain the state for which new positions in a manifest have been deleted, and still make sure that the metadata footprint isn't really high. Yeah. So what's next? One challenge is we want to be able to define like expressions so we can store stats on derived columns. So this expressions has like spanned so many things, like generated columns. How do we represent partitioning information? It also spans like fine-grained access control, like not even related to the v4 spec. So that's something we want to work on, because I think it's like a very core primitive to like a lot of things in the project now. One kind of discussion is like inline versus out-of-line manifest DVs. As proposed, they're primarily inline, but there might be certain cases at scale where you need to actually flush the manifest DV out to a file. Another open debate is like, what do we do with the partition tuple? Really only need these values when trying to match against equality deletes. Arguably, you can get the same level of pruning just by storing stats on columns, because all partition transforms are just derived from columns anyways. So there's like a lot of stuff there. And lastly, I think we do want to define a clear algorithm for change detection. We've done all the like cases, but I think it would be helpful for the community if we probably defined like a very clear change detection algorithm. I think that's probably like something that's hidden in the current implementation, and it's probably better to be very clear about like what the effective change detection algorithm would be in the new structure. Yeah, and lastly, I want to give a huge shout out to the community. Like I said at the beginning, I'm like looking at the crowd. It's absolutely incredible how the community has grown over the years. Want to give a shout out to folks from Snowflake who also had a single file commits proposal. Russell, Steven, Yifeng. Yeah, it's been really great collaborating with them and sort of getting to work on the next phase of the project. So yeah, thank you.